Hey everyone, welcome back to your CS50x adventure. This is week 5 where we dive into data structures, the essential tools for organizing data efficiently in memory. We explored how smarter structures like queues, stacks, and trees help us store, access, and manipulate data faster and better. Let's start with the queue, a simple yet powerful structure. It operates on the FIFO principle, first in, first out. Picture a line at the bank, where the first person to arrive is the first to get served. We add items by enqueuing them to the back and remove items by dequeuing from the front. This predictable order is everywhere, from managing print jobs to scheduling computer tasks. Next up are stacks, which follow the LIFO principle, last in, first out. Imagine a stack of plates in a restaurant kitchen. The last plate placed on top is the first one you take off. You add an item using push and remove it using pop. This structure is perfect for features like undo in software or your browser's back button history. Now, arrays are fast for access but rigid, requiring one large block of memory. To gain flexibility, we use linked lists. In a linked list, each element, called a node, holds a value and a pointer to the next node. This lets us connect memory wherever it's available, not needing one big chunk. Sure, we use a bit more space storing those pointers, but the flexibility gain is huge. In C, we access a node's value using node arrow value, which is cleaner than star node.value. But searching through a linked list can still be slow. That's where trees come in, specifically binary search trees. Each node holds a value and has two pointers, one to a left child node and one to a right child node. If a new value is smaller than the current node's value, it goes to the left. If larger, it goes to the right. This organization makes search super efficient, taking O of log n time, provided the tree stays balanced. Trees give us a great combination of structure and speed. Moving on, we explored dictionaries, which store key-value pairs. Think of dictionary at index name, returning John. Under the hood, many dictionaries rely on hash tables. Hash tables cleverly combine arrays and linked lists through bucketization. A hash function converts a key, like a name, into an array index. This lets us jump straight to the correct bucket instead of searching everything. But there's a catch. Collisions happen when different keys hash to the same index. We solve this by using a linked list inside each bucket to chain the colliding items. A smart hash function, using tricks like ASCII values or prime numbers, helps minimize these collisions. For even faster lookups, we can use tries. A trie is like a tree of arrays where each node represents one letter in a word. For the word cat, you'd follow the path C, arrow, A, arrow, T. Lookup time then depends only on the word length, O, of K, where K is the length, almost like constant time. But this speed comes at a cost. Tries often use significantly more memory, sacrificing space for time. Our project this week was building a spell checker called Speller. The task was to load a huge dictionary into memory, typically using a hash table. Then, we scanned a text file to find and flag any misspelled words. We had to implement the load function to read the dictionary file. We also needed the check function to verify if words are in the dictionary, and we wrote the unload function to free all the allocated memory correctly. The real challenge was crafting an efficient hash function and managing memory like a professional. This project was a crash course in performance, optimization, and mastering data structures. So that wraps up week 5 of CS50x's. We moved beyond theory into real-world structures powering everyday software. From queues and stacks to hash tables and tries, we now have the tools to make data dance efficiently. If you're finding this series helpful, drop a like and subscribe for the next deep dive. Until next time, keep coding, keep learning, and remember, data structures aren't just academic theory, they're practical tools you'll use constantly.